See, magnetic field is something, I think it sounds something similar to electric field. So electric field we can sense in terms of force experienced by a charged particle. Similar way we have already, I think all of you have experienced magnetic field. And very common way we can experience magnetic field is the way the compass behaves. I think all of you must have experienced a compass. What happens when we place the compass? It comes to particular orientation. It has a tendency to point in the direction of magnetic field, which normally is Earth's magnetic field. So what was also observed, see, suppose if you keep a compass here. Suppose earlier there's no current here. So in this case, what this line shows here, this line shows a current carrying element, and current carrying element is also moving charge. So this chapter is about the current carrying element or moving charge produce magnetic field. How it was first time observed, if you think of a simple experiment, it was something like this. So suppose you have a magnetic needle or compass. If we place it at any place, it comes to and points in a particular direction. And that direction gives the direction of what we call as north direction. Actually, it's the direction of magnetic field at the point where the compass is placed. What is observed when no current is flowing, it points in a particular direction. But when the current was set up, when this compass was placed near to a current carrying wire, as soon as the current starts, it was found that direction of needle changes. So which definitely indicates in addition to Earth's magnetic field, some other magnetic field also has come into effect, and which is due to flow of current. So now next 3-4 days, our focus is to understand how to calculate magnetic field due to current carrying element. Okay, so we consider a wire which is carrying current I, whatever, some irregular shape the wire is, and okay, is carrying current I, and we can calculate field similar to Coulomb's law. We can calculate magnetic field using Biot-Savart law. Biot-Savart law defines magnetic field due to an infinitely small current carrying element. Similar to the point charge there. So this one is not for long element. The law is for a very small element of infinitely small length. Infinitely small length, even if the wire is curved in shape, if I take a small element, it becomes like a straight element. And in some way, we can treat as a point as well. So consider an infinitely small element, and we define that this is a small element. And we define this small element of length dl vector. So even the length also is taken a vector, and its magnitude would be its length, and its direction of this length vector is in the direction of current. Okay, so this is this small length, and though we have shown it like this, it's extremely small. It could be taken as a tangential to wherever it is placed. Okay. Suppose we want to find out some general point P. I want to find out what is the field created by this infinitely small element having current I and length vector as dl, some point P. How do we define that point P? That point P has a position vector r bar. Position vector, for any position vector, we need to choose a reference point. So what is the with respect to what? This is with respect to the small current element. Since the length of the current element is very small, it can be taken as a point. So what is the reference point is taken as position of the current element, or midpoint of the current element is taken as the reference point. And midpoint also meaningless because length is negligible. So this is the position vector r. So this point P. So what is the field this point will experience? What magnetic field this point will experience due to this small element is given by Biot-Savart law. And Biot-Savart law looks like this. Okay, let's try and understand. So major focus is going to understand what is magnetic field at P due to current element. This, since current element is small, we write as a dB, which indicates small magnetic field. It has first term. We can think of the first term as a constant. The first term is mu naught by 4 pi. The current is I, is a cross product. So which makes to understand direction and magnitude, we need to recall our understanding of a cross product. It's a cross product between two vectors. Which are the two vectors here? Length vector and position vector. So it is I dl cross r divided by r cube. R being the magnitude of, r is the distance of the point from the current element. Okay, so let's try and understand better what is the term mu naught. Mu naught is a new term here. And mu naught is called permeability of vacuum. Is a property of the space, something similar to epsilon naught, which refers to permittivity, and this is permeability. And there also we take, in case of electricity, we take that constant value is 9 to 10 to the power 9. So this whole term here, which is a constant, mu naught by 4 pi is equal to 10 to the power minus 7. And unit is Tesla. Tesla is a unit for magnetic field. So mu naught unit is Tesla meter per ampere. So this current also comes in. Okay, so Tesla is the unit, SI unit for magnetic field. So we'll try and understand this term better. This looks a little bit scary. So what is this field? This formula, you should commit to your memory. I think more than this formula, I think it's better to break it into two parts: magnitude separate and direction separate. Let's try and understand here what is the magnitude now. So in terms of magnitude, when you write what is this term equal to, whenever you take cross product of two things, its magnitude is equal to what? I could have written as magnitude as I is same into dl is the length into r into sine theta. Okay, so one r gets cancelled. So this term in terms of magnitude is equal to mu naught by 4 pi I dl sine theta divided by r square. So this also follows inverse r square law, similar to many other cases like gravitational field, electric field. What is theta here? Theta is angle between two vectors involved in cross product. Theta is angle between two vector parts of the cross product. Which are the two vectors? One vector is dl vector and other is r vector. So what is the direction of dl vector? So if I draw a line along the dl vector, so this is the direction of length vector and this p vector, and this angle between them is theta. So this is what cross product is. So let's understand here. So if I take a point P, had I taken a point P here, the theta would have been 0. In that case, the whole quantity would have been 0. Where would this be maximum? So if I take a point perpendicular to this length here, theta will become 90. So theta will change from 0 to 90 as we move from here to here. And as we move further from here, it will change from 90 to 180. At this point, theta becomes 180. At this point, theta is 0. Perpendicular theta is 90. So we understand what theta is. Theta is the angle between two vectors involved. Two vectors being length vector and position vector. Position vector of point P. Position vector of what? Position vector of point P, where we want to calculate magnetic field. We are interested in calculating magnetic field at point P, and position vector with respect to small current element vector. So this is magnitude. Let's understand direction. So since the direction also nothing new, if you understand what cross product is, so its direction is given by property of the cross product. Let's recall what the cross product is. How do we find out cross product of A and B? We use right hand thumb rule. In case of right hand thumb rule, direction based on right hand thumb rule, rules of cross product. So in this case also, there are two ways of thinking would be. One way to think, if we apply the known method, how our fingers should curl from the first vector to the second vector. So you should curl your finger in this fashion. So just all of you try to curl your finger in this fashion, and the direction of thumb will give the direction of magnetic field at point B, not here. Which point field? Field at this point. If we curl our finger in this direction, what is the direction in which the thumb points? Can you find out? Can you do that one? Can you see on your screen? Can you turn your fingers, curl your fingers in the direction of the arrow from the first vector to the second vector, and see which direction does your thumb point? And some of you, if you recall the properties of the cross product, even before I find the direction, what I must understand, the cross product always lies in a plane perpendicular to the plane containing two vectors. So which are the two vectors here? These are dl vector and r vector. If two vectors are like two lines, two arrows, start from the common point, and unless they are collinear, they'll always have a unique plane containing these two. So in this particular case, plane of the screen or plane of the paper or plane of the drawing is the plane which contains dl vector and r vector. So hence cross product would always be perpendicular to the plane. So perpendicular to this plane, how many directions are possible? How many directions possible perpendicular to this plane, plane of the figure? Only two directions possible. One is into the plane, one is outside the plane. Towards or into Okay, so in this way we curve, which direction it will point? Which direction will the thumb point? Will it
Into
point
the
towards you or it will point away from you? Will it be into cross kind of thing or will it be dot kind of thing? All of can easily spot. If I
cross.
curl my finger, it points into the plane of paper or into the plane of drawing. So the direction of feel at this point will be like this. This is how we denote cross. Cross indicates going into the plane of paper. Okay, and we use some other rules also. Another way to find the direction. See, another way of thinking, if there's a current element, this right hand thumb rule is this is also one method you can find. You place your thumb along the direction of current. So any current element, just you hold the current element. Imagine holding the current element with your thumb pointing in the direction of current. The direction in which your fingers are curling in this direction. This is the direction in which the fingers are curling. This gives the direction of magnetic field. So if this is the current element, magnetic field around will make a circle, and all these circles will be in a plane. Which plane the circles will lie? Circles will lie in a plane perpendicular to the, so the plane will be, or other way of saying, the plane containing this magnetic field will be perpendicular to the current element, or all the circles what we see here, the current element will form the axis of these circular fields which are formed due to straight element here. That's one way. So we can use the property of the cross product, or I can use this also. I can imagine holding the conductor with thumb pointing in the direction of current. The direction in which the fingers curl indicate the direction in which the magnetic fields are. And we easily notice here magnetic field, unlike electric magnetic field, they formed a closed loop. And we'll see from energy perspective later why they can form a closed loop despite being centered. Another way to visualize is, suppose this is something you want to get a three-dimensional perspective. If I want to get a three-dimensional perspective, see, this is a small element. This is a small element because of which I want to find field at different points. I want to find what is the field at this point, what is the field at this point, what is the field at this point, and so I marked 6 points here. One thing what unique I find, the plane in orange color. Plane in orange color contains the length element and the position vectors of the 3 points, all lie in the same plane. So the field at these points will be perpendicular to this orange color plane. And if I find the right hand rule, how the fingers will curl, if I look from this side, fingers will curl. If I hold my thumb, keeping this thumb in this direction, fingers will curl downwards. So direction of field, this will be downwards, this will be downwards, this will be downwards. Similar way, I want to find field at this points. So this point, and this point. So whichever first, suppose I want to field at this point here, I can visualize a plane containing this vector and this vector. So which is the plane containing these two vectors? This rectangular plane contains those two vectors. So field will be perpendicular to this plane. Which direction the field will be? This is the direction of the field. And if I place myself here, if some observer is standing here, how would this observer see this current element? Will it current element look like a dot or a cross? Is the current coming towards him or going away from him? If I imagine the current element like an arrow, what will the current element look like? If I stand from here, the current element, I will see just the tail of the current element, it will look like this. And how would this, if this is the current element, this point will be like this, direction of field at this, all these points will be like this. And the points which are coming in the same plane, direction of field will be like this. If I draw the field lines, if I look at the field line standing here, the field lines will look like this. It will go in a, it will form a circle. And it will form a circle, and this will be the direction of arrow. So at this point, what is the direction of field? At this point, this is the direction of field. At this point, what is the direction of field? This is the direction of field. So at any point, I can find out the direction of field. So this is something understanding directions. I'm giving the different examples so that understand direction better. Another way to understand here, so this is the point here. So suppose I draw a circle. If I draw a circle here, dotted line, all points are equidistant. Okay, all points are equidistant. So distance is same. So when the R value is same, but does it mean that all points which are lying on the circle will the magnitude of field be same and direction be same? Let's try and understand one by one. So this is a point, this is a current element. I want to find field. I have selected drawn a circle with the current element at center. So all points on the dotted circle are at the same distance. This term is same. dl is same, I is same, these constants are same. Only thing which is changing is the sine theta term. So what will the and based on the sine theta term, and second thing, the direction term. So what will happen, any point which is lying on the right hand side, not only this point, this point, this point, at any point if I take here, the fingers will curl in this direction. So any pair on this here also the direction of field will be like this. Here also direction of field will be like this. Here also direction of field will be like this. In all cases fingers are curling in the same fashion. So all the points on the right half of the circle, the direction of field is perpendicular to the plane and into the plane of it. And what would the field at this point here? At this point, sine theta is 0, and no field. This point field is 0. This point field is 0. So if I look at which point will the field be maximum, can anyone spot which point will the field be maximum? If I mark this point as A, this point as some point here as B, and some point here as C, and some point as D. All points are equidistant, but which point will have the maximum magnitude of magnetic field?
Easy.
No, it's easy. Which point will have zero magnetic field? Point A. Any point which lies on the line of conducting element, the same line, will have zero field. This point has zero field, this point will have zero field. So as distance remaining same, as the angle keeps increasing until 90, field will keep increasing. And any point, what you notice here, any point I can divide the whole thing in two halves, right half and the left half. So assume that you are sitting in a car, you are facing this direction, you're facing the direction of current. This entire space is right part and this part is left part in this plane. And any part, anything which is on the right hand side, the direction of field is into, and left hand side direction is out of page of paper. This is into the plane of paper. So this is how we can again one more example we can understand. Okay, let's look at some more. Sorry. So I hope you are following so far. So let me come back to this point again. So you followed the point here. So whenever we take a plane containing length element and position vector, the field will be perpendicular as given by the right hand thumb rule. Okay, so let me again come back to this point here. See this here also, you see here, so this is the thumb rule. So I can imagine a plane. I have taken this imaginary plane. I have taken a rectangular plane, and where this rectangular plane contains this current element. So any point, suppose I take this particular point, what will the direction of field? What will the direction of field here? Everywhere again, since anywhere on the point, plane field will be perpendicular to the plane. It could be into the plane or this side of the plane. So since you look at the direction with the fingers are curling, all this point, the direction of field will be like this. This point also direction of field will be like this. Suppose we take a point here. This also field will be perpendicular to the plane which you have been drawn here. But which direction? The direction of field will be, see fingers are going into the plane of paper, the direction of field will be like this. The direction of field is like this. Okay. Similar way, let me check in this case also, let me check a one more plane. Where is one more plane? This is one more plane. So I have taken a rectangular plane. Here also, so since this plane and current, they lie in the same way. So which direction, if I have my thumb pointing in this direction, how my fingers will curl? Fingers will curl like this. Fingers will curl like this. So at any point, if I take, what will the direction of field at this point? What will the direction of field at this point? What will the direction of field be there? If this is a plane, it will be perpendicular to plane, and it will be like this. It will be like this. So understanding the direction. So it will be perpendicular to the plane containing dl vector and r vector. So if I draw a plane which contains this length element and also the point at which the field has to be calculated, it will be perpendicular. Only two directions possible perpendicular to plane, either into or out of, and into or out of we find out using right hand cross product, right hand thumb rule. Okay. So magnitude and direction. So this is okay. So this is, I hope again to recall, this is the point, and I hope we have understood. Understanding, we need to clearly understand which is the current element we are taking account, which point we need to calculate, what is the position vector, what is the theta, and what is the distance, and we can apply the formula and we can easily calculate. Okay. So all points in the plane containing current element and point P, R vector, the field will be perpendicular to the plane, either into or out of. So moment we exam also or anywhere else we come across a question where figure is drawn in this fashion. Moment figure is drawn, it means plane of the figure contains dl vector and r vector. So any point in this plane of figure, the field will be either into or out of. So I can represent field at any point in this planes, either in direction of field in terms of dot or a cross. Dot will indicate anywhere on the right, so it will be into. So any point on the line of current element, field will be, so any point on the line of current element, field is 0. Facing the direction of current, field at any point on the right will be into. So assume that you are moving in the direction of current, you are sitting in the car. If you are sitting in the car, everything, this is on the right hand side, and this is on the left hand side. If I move along the direction of current, and if I imagine myself moving in a car along the direction of current, any point which lies on the right hand side, the field will be into. So anywhere in this entire half space, I have divided plane into two parts. On the line, field is 0 everywhere. On the right hand part, field is in this direction. Anywhere on the left hand side, the field is out of the plane of paper. Simply right hand thumb rule. If I curl my finger, if I place my thumb in this direction, fingers will curl like this. It will go into the plane of paper, it will curl out of the plane of paper or a plane of drawing. So this is a very simple important point. Whenever we come across a situation where figure is drawn, and figure which has been drawn is not in 3 dimension, is a plain 2-dimensional figure, and 2-dimensional figure contains the point at which the field has to be calculated. It also contains the current element. In that case, field at any point except for the point lying on the line will be perpendicular to plane of the paper. So I can indicate the direction, and which is very common way to indicate direction. If it is into the plane of paper, perpendicular, only 2 directions possible, either dot or a cross. Cross is into, dot is out of. Into is right, everything right hand side into, everywhere in left hand side is out of. So I can, this simple thing I can represent like this. So, this is something, so here this is current element, anywhere on the right space into, anywhere left space out of, cross and dot. That's how find the direction. So magnitude and direction. To find magnitude, so I need to represent two of them as a vector and draw as a line, and angle between two vectors, tail to tail. Vectors must be placed tail to tail. Angle between two vectors, dl vector and r vector, is a theta, and we can calculate magnitude separately, and we can find out directions. If we identify the plane containing two vectors, then field is perpendicular to the plane, 2 directions possible, out of or into, and out of into we can find out whether it's right hand side or left hand side. Right hand side facing the direction of current, any point lying on the right hand side, field is into, any point left hand side, field is out of. Any questions so far? This is basics. I have repeated number of times. This basic you go through again. Yes, Vignesh.
So now this concentric circles and all that field which we are talking about, it's only due to this one element, right, sir?
There's only one element. The formula is only for one element. We'll come to more later. First, we need to understand one element, and one element is understand, then only can understand the rest of it. The starting point is one element. And what is the length of this element? Negligible.
Yes, sir.
That's why even curved, even if wire is curved also, if you take a small element, it could be treated straight and it could be represented by a vector with a unique direction. Had it been longer, it will not have a unique direction. Anybody has any other question? Okay, so basically the magnitude separately, because sometimes vectors we find a little difficult. So magnitude, this is how we calculate magnitude, and commit this formula into a memory, not very complicated one, constant into I into length into sine of angle between length and the position vector, and this is square of the distance.
How did we arrive at that, sir? The law?
Law, nothing. This is something, all this law, experimental law. So what we do, mother, we have a current element, we place this magnet at different elements, so some method we calculate the field. And see, most of this thing here, it follows certain principles. So it is expected, people would have anticipated it will follow inverse law. And what we find when you make the distance twice in the same direction, effect of field becomes 1/4. Okay, easy to conclude this inverse law. This is all experimental law. Experimental law, you understand what experimental law? Experimental law is observation of natural phenomena and converting this observation into a mathematical relationship. Same thing, gravitation. Is there any proof for gravitation law? There's no proof. But this is something you conduct any number of experiments, you found it is holds true. So it is just observation of what happens naturally And all those observations, can we capture all this observation, different behavior, different observations, different experiments in a mathematical relationship? If you find that mathematical relationship always holds true, that becomes an experimental law. So this also is of the same nature. We don't know, no proof, no derivation. Okay.
Sir?
Yes.
So now at point P, what will be the nature of the magnetic field lines if we draw those concentric circles?
Yes.
Like,
see, first of all, or any field line due to this element, all field lines will be circular in nature, and the axis, this length element will always lie on the axis of the circle.
yes, sir.
Okay. So suppose I take a view from here. I stand here and look into this. How would this current element look like? I hope you follow. A current element, it will look like a cross. It is current is going away. So anything if I draw at this point also P. So I take a place on P. From here, everything will look in place. So whenever I draw, it will look like a circle. And where the axis of circle is lying?
Along the direction of the current.
Direction. And something, suppose you want to understand, that's why I have kept this one. This figure also gives a good indication. Just try. I have collected figures from different places and it presents in a different way. So different, we try to visualize this current element, how the field line will be. See, if these 2 points, will the magnitude of field be equal? These 2 points? If they lie in a plane perpendicular to this current element, magnitude of field at this point and this point be equal because the distances are equal.
Yes.
Angles are equal. Okay. So if I take, so if I from this point, if I take let's say if this distance is also some d and this distance also is d and this distance is something. So what will happen? Magnitude of these 2 point field will be equal and they will lie on the same field line. Okay, into and out of. Any point, and this is we have arrived at. Let's come to the second part, direction. So we understood what is right side and what is left side. And left and right depends on orientation. Suppose you take another element. I take another element. This element is like this. So the second element, are we clear which is the right direction, which is the left direction? For second element, if you imagine if you're traveling in this direction, this side is right direction, cross, this is left. So if I take second element, this is how the field will look like. Similar way, if I take one more element here, like this and like this. So what will happen? See, if I combine all 4 elements, what do we see this one? If we combine all things, it makes like a, what kind of loop? Clockwise or anti-clockwise? How does it go?
Clockwise.
Clockwise loop. And what we find here, all this, what is common about all points lying on the right hand side of the direction of travels? They are inside the loop. So if it is a clockwise loop, what I notice, another way you can interpret the result is, if it is current element is making a clockwise loop, any point inside, it is field is cross, any point outside is dot. Okay, so if current element forms a loop, at all points inside the loop, field will be in the same direction. Is it not? Field will always be in the same direction when it is forming a clockwise loop. I hope you understand why the field will be in the same direction. Loop lying in a plane. Okay, so everywhere, which direction, you can think in terms of thumb also. You hold your thumb in this direction, how the fingers go, every fingers inside will curl in and out, this side will fingers will curl out. All of you, if you want to try, you hold a pen in place of current element, hold a pen with the nib pointing in the direction of the current and see which direction your fingers curl. All of you can do that on your own and see that you understand how the direction is formed. So whenever a loop is there, this is a plane of the loop. So anywhere in the plane which containing the loop, anywhere the field will be perpendicular to the plane. Yes, Alan.
Sir, if we take the direction of the, tangent to the direction of the magnetic field at the points which is symmetrical, we'll get a different angle, right?
See, if all the loops are combined, okay. See, if I take a circular element also, okay. If I take a circular element, just argue your point here. So let's take that one. Suppose let's just quickly discuss this point. Okay. So let me take Bella, the 2 points I'm taking. This element. Suppose I take this element. I want to find field at this point. Will the field at this point due to this current element, would it lie in the plane of drawing or will it not lie in the plane of drawing? Tell me. The current element lies in this plane of the drawing and r vectors lies in the plane of drawing. It means field due to small element is perpendicular plane of paper, and this is the direction. What is the direction of field? Direction of field will be like this. Suppose I take another element here also. This element also lies in the plane of paper or plane of drawing, and r vector also lies plane of the drawing. So again, due to this element also is perpendicular. Which direction? Cross. So whichever point I take, different elements may have different magnitude, but all elements create field in the same direction. So anywhere, if I take a circular loop, anywhere inside the circle, what is the direction of field? Everywhere the direction of field is perpendicular to plane of the circle. Is this point understood, Alar?
Yes, sir. We're taking only points in the plane. Right?
Yes, we are taking the points of plane. So I'm talking about which plane? The plane containing the loop. So any point on the plane containing a loop, if I take a circular loop, any point inside the circle, what is the direction of field? Perpendicular to the plane of circle. Any point, if I take a circular loop, any point on the plane of the circular loop, if I take a point, what will the direction of field? If this is the direction of current, what will the direction of field? Anywhere inside the circular loop. Is every single element creating field in the same direction or not? That's the point. Is the every single element creating the field in the same direction or not? If all elements are creating field in the same direction, resultant also will be in the direction which each element is creating a field in. Is this understood?
Yes, sir.
All, everyone?
Yes, sir.
Okay. So let's proceed further. So same direction, correction loop. So this is something seen in addition to small element. One more thing I understood, if we treat any loop as several small elements, I'll give some more visual also. So if this is the kind of loop, you just think of that any element if I take and any point I choose. If I calculate direction of field, at any point inside the loop, direction of field comes same cross. And since every small element creating the field in the same direction, if I take the entire loop also, direction of field will be same. So if I take a loop, another way you can think of this also we can apply. Sometimes we use a right hand thumb rule. We extend a right hand thumb rule for circular loop. What do we say here? If we curl our fingers in the direction of current, can you curl your fingers in the direction of current? Right hand, take out your right thumb. Curl your fingers in the direction of current. Which direction does the thumb point? The thumb will point into the plane of paper. Something like this. So this also, everywhere we talk about, I started a right hand cross product, also right hand thumb rule. Previous case, straight element also we used right hand thumb rule. Here also we used right hand thumb rule. Everywhere we will not even go to left hand. Every time we use right hand thumb rule. So what is the direction of field? Either I can take a small element and whenever it is clockwise, in the interior region, it will be cross. You can think in terms of, you curl your fingers in this direction, your thumb will point into the plane of paper. So this important point, if we have a loop which lies in a plane, any point, if I draw a plane containing that loop, if loop lies in a plane, so if you draw a plane containing the loop, inside the loop, field will be in one direction, outside the loop, field will be in the opposite direction. And if you have to visualize field lines may be something like this. In three-dimensional space, field lines will look something like this. So if there's a circular ring in the space, how the field lines will be? If the current is going like this, field lines will be like this, going up and out. So all field lines here, this will be inside, it is going up, outside it is going down. You visualize in 3 dimension what is happening here. So these are different figures. So you try and understand each figure, you will get better clarity. Similar way, so how would the field line look like if this circular loop? Field lines will look like this. This is how they'll form a loop. This is how the field lines due to circular line will look like. But look at all the field lines lying in the plane of the circle. When they are in the plane of circle, all are having pointing upwards. But as we go further, yes, it will not keep remaining straight, it will vary. And why they are spreading out? Here we find the spacing is much less. Here spacing is more. What does more spacing indicate here? Here field strength is more. As we give away, spacing between field lines keep increasing. Field strength will keep on diminishing. So if this is the current loop, I can think of, you see three different hands. All of you can notice there are 3 different hands. What are 3 different hands? Notice here. See, all cases are applying right hand thumb rule. Thumb is along the direction of current. Which direction the fingers are pointing in the interior region? Fingers are pointing upwards. Here also, if I have thumb in this direction, which direction fingers are pointing? Upwards. So Anywhere outside, if you to look at this viewpoint, anywhere you find the fingers are pointing upwards, right hand thumb rule indicate direction of field. In this case, any point in the region within the circular loop will be this. This is the direction of field. Yeah, field strength may not be same everywhere. Field strength may vary, that we don't know. But direction of field in this plane of the loop, a plane of the circular loop, within the circular loop is one direction, outside is the opposite direction. That is inside one direction, outside is opposite direction. Okay, now let's see whether how do we apply so that we get a better understanding of this. Suppose we take a circular loop, current element of in form of arc of circle radius r at carrying I. So this is not a full circle, it's an arc of a circle, current I, radius r. We want to find out field at its center. And we can find field only at the center, other field is too complicated to derive. How do you find out field at the center? I want to find field at point P. Can you think of step-by-step method to find field P? I only know the formula for a small element. So what is the first step I must take? What should I do to find field U2? This is not a small element. So since I know the formula only for a small element, I need to visualize this arc of a circle as several small elements. So let's take one small element. Consider a small element of length dl, which makes an angle d theta at the center. So this is small element, okay, and it makes an angle d theta at the center. So length becomes r d theta. Okay, this length is r d theta, and this is the direction of current. Can we find out field at point P due to this small element? Let's see, can we apply the formula and find out? This is my formula. What is the formula for magnitude? First of all, direction. Direction I find out using right hand thumb rule. Direction due to right hand thumb rule, I find out the direction of field will be like this. Direction is into the plane of paper. What is the magnitude? Magnitude is constant into current into length of the element into sine of angle between the two divided by r square. Do we know all this term here? What is dl here? dl we already mentioned, dl is equal to r d theta. Important point, what is angle theta here? What is this angle theta here? Can someone point out what is the angle theta?
90
angle,
degrees.
90 degree. Angle theta is this along the length vector, which is like this. This is the dl vector, and this is the position vector. Which is direction of position vector? This is the direction of position vector, r. And angle, since it is angle, angle is 90 degrees. So that's why sine theta becomes equal. Sine theta becomes 1. So that's a field due to a small element. Other thing what we notice, if I take every small element, it's a vector quantity. So unless all the magnitude, all the fields are in the same direction, I cannot directly add. In this case, just imagine if I take any particular element, all the direction of field at point P is same. Hence, direction is always into. Hence, I can vector sum also is equal to algebraic sum. So what is resultant field? Resultant field is simple addition of this quantity. What is simple addition of this quantity here? Okay, let's say this is all into place. Direction of field due to all elements are same. Hence, the vector sum is equal to algebraic addition. So we add this up. Rest all is common. Only term is d theta. So if I add up, what is we are adding? This one r gets cancelled. It's d theta. So what is addition of all small angle? All small angle is actually the angle the arc subtends at center. So summation of d theta will be angle subtended at the center. So what is my formula? Formula is this. What is magnetic field created by arc? This is constant term. Always keep in mind this is something like a constant term. Okay, and I by r. And what is the theta? Theta is angle subtended by arc at the center. So that becomes my formula for arc of a circle, which is extremely simple derivation. So far understood. Pranav Soma, have you followed so far?
Yes, sir.
Anvita?
Yes, sir.
What is this with very low voice, sir? See, sometimes you say yes in a manner, it sounds like no only. Okay, but anyway, we'll go through this in work session quickly again. And I would expect all of you, if you're not understood, just go through this file before the evening session. So Kevin, have you followed?
Yes, sir.
Okay. So you understood this. How did you arrive at? Is there something to memorize in this derivation, Kevin?
No, sir.
Pretty simple. You understood why
Yes.
this, what is angle theta, the small elements all are in the same direction. We can directly
Yes,
add
sir.
it up. So Kevin, can you tell me what happens suppose it's a full circle? Can you tell me what is the magnetic field at the center of circle of radius r carrying current I?
Sir,
Not
the
at the arc of a circle. If it is a full circle, what change will happen in this formula?
theta will become 360. Sir.
Not 360. It will become something else. We are using, when you written r d theta, theta has
2
to be
pi.
radian. Theta has to become 2 pi.
2 pi.
Yeah. Only thing what will happen, theta will become 2 pi. If it is semicircle, I'll substitute pi. If it is quarter circle, I'll substitute pi by 2. If it is full circle, we'll substitute 2 pi. So any arc of a circle kind of current element, we can easily find out what the field is, and direction of field is given by right hand thumb. Our fingers curling along the direction of the arc of a circle, thumb will give the direction. Of course, it will be perpendicular to plane. So in case of circle, this becomes 2 pi. It becomes equal to mu naught I by 2r. That becomes the formula for full circle. And when I have to memorize, easy part is the constant into I by r into theta itself in the center. So this is 2 pi, quarter circle, any shape, as long as we know the angle, we can easily find out field due to current element which is bent in form of an arc of a circle. Right, okay. And if it is, this is something again you can think of, if this is direction of current, if you curl your fingers in this direction of right hand, if you hold your thumb will point into the plane of the circle, and this is the nature of field. So anywhere the field this is, and due to circular element, we can calculate field only at the center. Can we calculate field at any other point? No. Here also we can calculate field only at the center of arc, not at any other point. And later on also we can't find out calculate field, that becomes too complex, chemical keeps changing. We can calculate field only due to one arc of a circle only at its center, not at any other point. And mu naught I by 2r is the formula. If you remember, this is much better, constant into I by r into theta. That's the field. Okay, field due to straight current element, carrying current I. In this case also, even before we start, important point to notice here is, if I take any small element, all elements, direction of field created at point P is same. All fields create which direction, into or out of? What is the direction in which the field is created at point P? If I hold my thumb along the direction of current, assume that the line of current is like a pen. If I may hold thumb in the pointing towards right, my fingers will come out of the plane of paper. So this direction of field here at point P will be dot kind of thing. Okay. So let's understand field at point P. What is the method I'm going to use? So in this case also, let's define the question. So from point P, and if I drop a perpendicular distance of point P is equal to d from the straight element, and angular position of two ends, something similar. Left hand, if I take anti-clockwise as positive, this makes an angle of minus beta, and other is making alpha. The plus alpha and minus beta are the angles made by two ends of the current element at the point P where field has to be calculated. What is angle alpha and beta? Angle made by the two ends of the straight element made at point P with respect to the perpendicular. So first of all, I have to drop a perpendicular. With respect to perpendicular, they could be in the same direction or they could be in the opposite direction. If they're in the opposite direction, one is positive, one is negative. If both angles are in the same direction, it would have been positive. Okay, so this is a angular position. Now let's see how do we solve this. Again, method of solving is similar. We have done a similar derivation in case of current, in case of electric line charge. There the direction was changing, it was more complicated. This is relatively simpler. We'll consider a small element. What is small element? Let's take a small element. This is small element we have taken. Okay, and this is small element, let's say this angular position, this makes an angle theta. And this is one, if you connect other end also, this has a d theta. And its distance also from here, let's say its distance is x and dx. What is the length? Length is dx here. This element we have taken. Okay, so here also when you look at, can we calculate field due to this element? Before we start calculating field, I will just write four things. What is the angular position of the small element? Angular position is theta and theta plus d theta. So the left end is angular position theta, right end is theta plus d theta, or angle subtended by the small element at point P is equal to d theta. And x is the distance from foot of the perpendicular, okay, and d is the perpendicular distance here. So what I find, x by d is equal to tan theta. I'm finding basically I want to convert this dx also in terms of d theta. So how do you convert that one? X is equal to d tan theta, and dx is equal to d secant square theta d theta. So this is something we had done earlier in case of electric field as well. So tan theta is equal to x by d, so that I deal with only one variable, not with dx. I will only deal with everything in terms of d theta. So let's first write what is the field. Can all of you write expression of field at point P due to this small element? Try and write that one. What is the field at point P due to this small element? Do you recall the formula? Mu0 by 4 pi is the constant term. I into length of the element into sine of angle between element vector and the position vector divided by the square of the distance. So can we write all those terms here? Okay. This is length of the element is dx. Angle is this a formula. Okay, let's substitute this value here. What is the length of element dx here? The length of the element dx also, I am substituting in terms of d theta, because everything I don't want to have two variables. We had discussed this earlier in case of electric field. So in place of dx, I substituted d secant square theta d theta. What is the angle here? Angle between them, if this angle is theta, this angle is 90 plus theta. This angle between two vectors, tail to tail. This is a position vector. Position vector of point P points in this direction. So angle between them is sine 90 plus theta. And divided by what is the distance r? The distance r also you can write in terms of d and theta. This r will be equal to d sec theta. So that's the expression. See that all of you it's clear, is simple substitution. This is expression of magnetic field due to a small element. And what is the direction? Direction of field is like this. And all elements will create field in this direction so that we don't have to take the components and then add. Since all fields are in the same direction, I can directly add. Algebraic sum is the vector sum. Okay, that's the direction of field. So what is dB? dB, okay, what are the terms which cancel out? One d cancels out. What is left in the denominator? D. I by d. So you notice here, I by d is the normal dimensions of field formula. Previous case in circle also we came at what is the formula for a full circle? Mu naught I by 2r. So this also matches with that, and that's cos theta d theta. This field element, so all elements are acting in the same direction. How do you find the resultant field? I'll take this, I'll integrate this one. So it will be integration of cos theta d theta. And when we substitute, yes, it will come into sine alpha minus sine of minus beta. So what do we look at this? This term is simple to understand. Mu naught I by 4 pi. I by d, d being the perpendicular distance. This is sine of two angles. What I understand here, simple terms, what I understand, if two angles are on the opposite side. Okay, so one will be positive, one will be opposite, one will be positive, one will be negative. This sign will become positive. In this particular case, what is making this sign positive? Okay, one of the angle is positive, one angle is negative. So two terms add up when angles are on opposite sides. And this is important to keep in mind in terms of only key part is, yes, should be minus or plus, though two terms add up when the angles are on the opposite side, as is the case here. Here what is fine, if you substitute theta beta is equal to minus beta, angle is minus beta here, clockwise, it will become positive. So we'll take up 4 or 5 examples of this so that is well understood. So what is the formula here? Constant into I by d. There was constant into I by r into angle at the center. Even in the state element also similar, constant into I by the distance. In case of circle, it was angle theta. In case of straight angle, it is either sine alpha plus sine beta or sine alpha minus sine beta. When would come some sign become plus? When they are in the opposite direction, it will become plus. When they are in the same direction, it becomes minus. Let's take some examples of this. I have taken 6 examples of this. Let's take one by one, practice with angles. So what we'll do in this case, I'll take 6 variations the same. All cases, current element is along x-axis. And the distance d is constant. All cases d is constant. So when I look at the formula, only thing which are changing are alpha and beta. So all cases, we'll only identify what should be this term. Should it be sine alpha plus minus? This term we need to identify each case. Let's do one by one. So this particular case, what does dotted line indicate? It indicates what is the alpha here? Up to how far it extends? Alpha is equal to pi by 2. It indicates it's a infinite wire of long length. It means alpha also pi by 2 and beta also pi by 2, and both are in the opposite direction. So should I add those things, or yes, both are in the opposite direction, hence I will add it up. So this term will be equal to sine of pi by 2 plus sine of pi by 2. 2 term. So what that becomes my formula for infinite wire. What is formula for infinite wire? Constant term mu naught by 4 pi. I by distance into this angle part. Angle part will come into 2. So pretty simple. Okay, let's look at the next one. In this case, what we notice here, where does this current element start from? We can call it semi-infinite wire. It's starting from foot of the perpendicular. So what are the two angles here? Do you spot two angles? One of the angle is
0.
One angle is 0. So one angle is pi by 2. Other angle is 0. So which makes task even simpler. So I'm just calculating this part here. So what will this part, angle part here? Angle part will be equal to sine of pi by 2. So what will my formula for semi-infinite wire? It will become equal to, again, let me write that term. How do we write that term? Mu naught by 4 pi, constant part, into I by distance, into sine of alpha plus sine of beta. Sine beta is 0, so it will be into 1. And it will be exactly half of this. So which basically means whatever field is created, this part of the wire creates same field as this part of the wire. Third case, let's do this one. What is the angle alpha and beta? And are they in the same? Should the sign be plus or minus here? So should I take here plus sign or minus sign?
Minus.
Minus sign. Both are
Minus.
flying in the same direction.
Same
So it
direction.
will come of this nature. It will be coming in this form. Sine alpha minus sine beta form. Beta, this is something. So plus or minus sign, I'll figure out whether they're on the opposite angles or same angle. And one of the angle here, larger angle is, one of the angle is pi by 2. What is the other angle here? Angle, how do I measure the angle?
Pi by 3.
Angle I measure with respect to the perpendicular. This is the angle. So what is the angle here? 30 degree. Okay, a by 3, so 30 degree. So I'll sub sine by 2 minus sine of 30 degree. So this will be equal to 1 minus
1 by 2.
1 minus 1 by 2. So in this case, this will be half of this. Okay. So what we understand from here, see, whatever field was getting created, this small length itself is creating the half of the total field. That's what it indicates here. Okay. So suppose I take wire of this length only, it will create a, so if I take, okay, you can follow that also. Let's look at this particular case. Extend from here, start from here, and extends up to infinity. Will it be plus sign? Will it be of sine alpha minus beta type or sine alpha plus beta type here?
Plus beta, sir.
Plus beta type. So first of all, both are on the opposite side. It will be of this nature, sine alpha plus sine beta.
3 by 2.
No, so what are these values here? Okay. So this values again, what is this angle? How do I measure the angle? I connect to this point. When I measure angle, I need two lines. One line is line connecting to the end, other is perpendicular. What is this angle equal to? 30 degrees.
30 degrees.
So I'll take again sine of 30 degrees. So basically 1 plus 1 by 2. So multiplicand here will be equal to 3 by 2. So again, those terms I'll multiply by 3 by 2. So pretty simple to calculate. Let's look at the next one. This one is extending from here to here only. So first thing what I noticed, should it be plus type or minus type?
Minus.
Minus type. Both are in the same direction. So first thing what you understand, it has to be of the type minus type. Larger angle first, small angle next. So this angle is 60 degree, this angle is 30 degree. It would be equal to sine of 60 minus because they are on the same side. Sine 30. That will be the multiplicand here. So pretty simple this also. Similarly, go to the last one. In this case, plus or minus?
Plus.
Plus. Both are on the opposite side of the perpendicular. So both are opposite side of the perpendicular. It will be sine alpha plus sine beta.
Sine beta.
What are the angles here? One angle is, again, how do I measure the angle? Just I've done 6 times, 30 degree. And what is this angle here? 45 degree. So it will be 1 by root 2 plus 1 by 2. Rest all, this term remains same. So finding field due to state element should not be a problem. So just see that all are understood. Anish, all are clear?
Yes, sir.
No problem at all? Any difficulty in this so far?
No, sir.
Shweta,
Yes, sir.
is it clear?
Clear, sir.
Very good. All clear. Okay, so green signal. So let's move on. Okay, let's try this one. Then find the field at the center of a square. So we carrying current carrying loop of side L. So this is square of side L, and we have to find field at the center. Length of the square side of this L. Can we all think and find how do you find field at this point P?
Yes, sir.
Yes, tell me what is the method?
So we can consider the four sides to be four different wires, and then the end the angular positions will be minus 45.
So basically, first point what you notice, all four of them are creating field in the same direction. They are forming loop. We had discussed earlier also. All create field in the same direction. Hence, if I calculate field due to one side, the resultant field will be 4 times the field created by one side. So all I have to do, I have to create only due to one side. Okay. And if I have to calculate for one side, okay, so this side I want to calculate field. Let's say this side is AB. Can I easily calculate field due to this side, one side AB? What I have to do first, which point I am to calculate field? I am calculating field at point P. So first what I do, I either drop a perpendicular or visualize a perpendicular. This is point P. And these are the angles it makes at point P. What are the angles with respect to the perpendicular? So this angle is also equal to 45 degree and this angle also is equal to 45 degree. So this is my formula. Let me first calculate field due to one side. Formula is this, mu naught I by 4 pi d. What is the d here? Perpendicular distance of the point from the line. What is the value of d I should substitute here? What is the perpendicular distance of P from the line? If length of each side of square is L, what is the length of the this side?
L by 2.
L by 2. So first thing, all four sides create magnetic field in the same direction. Owing to symmetry, the field will be equal due to each side. Resultant will be equal to 4B. B is the field due to each side. Let me calculate D is equal to L by 2. Alpha and beta is equal to pi by 2. Hence, this term multiplicand will be equal to what? The multiplicand will be equal to so sine of what?
2 root 2.
Pi by 4 plus sine of pi by 4. So pretty simple. This will be equal to root 2. 1 by root 2 plus 1 by root 2. So if I substitute, what is my final value? Mu naught I by 4 pi. And I in the denominator, we substitute L. So this 2 goes in the numerator. And in this also comes here, this root 2. So that's the formula for. So no need to remember. Yes, Arij, any question?
Sir, what will the DL vector of the corner point be?
Hey, see, corner point, no, I won't take as a corner. See, first of all, DL vector is not a point. So if I take any DL vector which is part of AB, if I take a small element, this also will be small element like this in this direction. I will not take an element which is partly in this side and partly in this side. Are you following, Arij?
Yes, sir.
I will break into A to be one part, and then if you have to calculate A and C, some part here, not these two together. Okay. So I hope this is what calculation Biot-Savart law is application. Simple part what we had done, arc of a circle, and we can extend for quarter circle, semicircle, and full circle. Similar, we had done field at a point due to straight element. And straight element also, I hope we have understood. Our only issue is perpendicular distance and understanding when will be plus sign and when is minus sign. When they are in the opposite direction, we take as positive and take this angle, sign of angle. Which are the angles? Be clear, because some books they give angle, some books use this angle. If I am using angle subtended by ends of the wire with respect to perpendicular, this angle I am referring to. Okay, so these are the angles, and it's easy to apply the formula and arrive at the final answer. So it should not be too difficult. So what we'll do now, again, evening session, by maybe 5 minutes, 10 minutes, we'll quickly go through what you have done, and we take up some more numericals, more applications of this particular formula and this particular application. Okay, so I'll stop here. So this is, I think our time ends. So anybody has any quick question, you can ask now. And else we'll anyway continue in the evening session.
Sir,
Thank you, sir.